Now we can talk about the proof ideas. Just to make sure I'm clear, I'm going to prove the following theorem that the loss of the greedy algorithm is at least 1 over 2d plus 1, and the loss of the patient algorithm is upper bounded by e2 minus d over 2 divided by 2, and the last line is just combining the two. And to be even more clear, I'm just going to talk about the ideas of the proof. There would be some technical steps that I'm going to skip and present them hopefully later in a technical video. And in order to prove this main theorem, it's important to understand the composition of the market under the greedy and patient algorithms to see how the market look like, what is the theme that we are going to analyze. Now, let's start with the greedy algorithm. Under the greedy algorithm, agents arrive continuously over time like this. And whenever I see an acceptable transaction like this, based on the rules of the matching algorithm, I immediately match them and they leave the market. Other agents arrive whenever I see multiple possible matches. Well, I pick one of them uniformly at random, let's say this one, and other agents come. As a result, the graph of agents, the pool in the market, so pool is the graph of agents, is always an empty graph. And note that empty graph is not a graph which has no nodes. Empty graph is a graph which has no links. So if I tell you that there are now 10 agents in the market under the greedy algorithm, you know that the structure of the network is an empty graph with 10 nodes. Now, why this is important? That's important because when I get the signal that someone is critical, I know that that critical agent is going to leave the market with probability 1 because there is no links in the graph. If there was, I would have matched them before. So the critical agents perish with probability 1. As a result, the perishing rate of the system, the rate by which someone leaves the market, is equal to this object here, which is the pool size. Why? Because the rate by which someone gets critical is just equal to the number of agents in the market. Recall that agents in the market get critical with rate 1. I normalize that rate to 1. And if I have k agents in the market, the rate by which some of them becomes critical is just k, equal to the number of agents in the market. And then the probability that a critical agent perishes is just 1. So the rate by which someone perishes is exactly equal to the pool size. Okay, now keep this in mind. We are going to study the composition of the market under the patient algorithm, and that's even more exciting. If I take a snapshot from the patient algorithm, I know that at each point in time, it's an Erdos-Renyi random graph. Why? And I will tell you what is an Erdos-Renyi random graph. That's because suppose this agent gets critical, then based on the rules of the algorithm, I look at the potential matches of that agent, which are these two, and again, based on the rules of the algorithm, I picked one of them uniformly at random, I match these two, and when I match them, they leave the market, and all edges connected to these two agents will also disappear from the graph. In particular, this red edge that I looked at, but I did not use, will also disappear from the graph because that edge was connected to the agent that I was supposed to match. As a result, the rest of the graph remains unexplored. I have never looked at anything in the graph at each point in time except at the moment that someone is critical, but immediately after match, the rest of the graph is still unexplored. This tells me that the pool under the patient algorithm is always an Erdos-Renyi random graph with parameter d over m. Recall that d over m was the probability that two agents are a match. An Erdos-Renyi random graph with n nodes with parameter d over m is simply a graph in which I have n nodes and each two nodes are connected with probability d over m. So if I tell you that under the patient algorithm there are now 100 people in the market, from the perspective of the planner, the pool is an Erdos-Renyi random graph with 100 agents and the probability of connection which is equal to d over m. Why this is important? Because of the next line. The rate by which someone perishes, the perishing rate of the system, is equal to to the pool size, which is the criticality rate of the system. So agents become critical with rate 1. So if I have k people in the market, if pool size is k, the rate by which someone gets critical is equal to the pool size. And then the probability that I cannot match a critical agent is simply equal to the probability that that agent has 0 matches. Now that agent is a match to anyone with probability d over m. That agent is not a match to an agent with probability 1 minus d over m. And the chance that that agent is not a match to anyone in the market is simply 1 minus d over m to power pool size minus 1. So let's keep this in mind, that the perishing rate under the patient algorithm is equal to the pool size times 1 minus d over m to power pool size minus 1. Now the proof, the real proof in the paper, which I'm going to hopefully record some videos to go through technical details, has lots of technical ingredients that I'm not gonna prove them here, but it's good to know what they are because they help us form their mind on what type of stochastic process we are analyzing. Now let's ZT be the number of agents in the pool size, basically how many agents I have in the market. This is a stochastic process in this model. And let's ZT just denote the number of agents in the pool at time t. Now, the first technical ingredient is that ZT is a sufficient statistic for the distribution of the trait network for the gradient patient algorithm. What do I mean? I mean, if you want to know what is the structure of the network under the gradient patient algorithms, it's enough to know what is ZT, how many agents are now in the pool. Why? Because under the greedy algorithm, if I know there are 10 people in the pool structure is just an empty graph. Under the patient, it's an Erdős-Rényi random graph. The second piece is that ZT is Markovian, and that's because I defined everything to be Poisson, so ZT it has the Markov property. Now the third ingredient, which is important but I would not prove, is that ZT converges very rapidly to a unique stationary distribution with the mixing time of log m log 1 over epsilon in epsilon total variation distance. So if I look at how long does it take, I mean, intuitively speaking, if I look at how long does it take for this stochastic process to converge to its unique stationary distribution, it's very, very fast. Okay, so forget about this total variation distance if you don't know what that is. In picture, this is what I basically mean. If I start from pool size 0, and the stationary pool size is roughly 1,000, it takes less than 2 periods for me to get very, very close to the stationary pool size and then remain around it. Now, the last technical ingredient that we have to prove in the paper, which we do, and that's actually the most important piece, is that this ZT process, the number of agents in the market, is highly concentrated around its expected value. What do I mean by that? I mean, by picture, that's what I mean, that if you look at the stationary distribution, with very, very high probability, you're almost always around the expected value of the pool size. And that's something that I'm not going to go through here because it's very, very technical, but you can find it in the paper, and hopefully I will do a different video for that. Now, given all these results, this is the big picture of the proof. Suppose ZT is highly concentrated around its expected value. That's something which I just claimed but didn't prove. Now, under the patient algorithm, we found out that the perishing rate of the system is this object here, which is pool size times 1 minus d over m to power pool size minus 1. This is just a few minutes ago. If you go back in the video, you can see that this is the perishing rate. I replaced the pool size by its expected value by using this concentration bound. I mean, in fact, I have some lower order terms here that I'm not showing you here because this is the overview of the proof. Now, this is the perishing rate. If I divide the perishing rate by the arrival rate of agents to the system, which is just m, I will get the steady state loss, the steady state fraction of the agents that perish and leave the market unmatched. For the greedy algorithm, the same thing goes through. If I divide perishing rate by the arrival rate, I get the steady state loss, the steady state fraction of agents who perish. And recall that under the greedy algorithm, the perishing rate was just pool size times 1. And the arrival rate is still m, so I have this expression here. Now, if you look, this expression here is an increasing function of the pool size. So ideally, the greedy algorithm would like to decrease the pool size as much as possible. On the other hand, this term here on the loss of the patient algorithm is a decreasing function of the pool size. So ideally, the patient algorithm would like to increase the pool size as much as possible. Now, the next step is to prove the following, that the pool size under the patient algorithm is at least m over 2. Okay, I will tell you some ideas of how to prove this in a minute, but if I prove this one and I put m over 2 into this equation, then I can show that loss is upper bounded by e2 minus d over 2 divided by 2. And the way to show this is very simple. Recall that 1 minus d over m to power m over 2 is upper bounded by e2 minus d over 2. So that's just the inequality that we know it exists. Now, in the next step, I'm going to show that the pool size under the greedy algorithm is at least m over 2d plus 1. And then if you plug in this bound into this equation, you can see that the loss of the greedy algorithm is at least 1 over 2d plus 1. Now there are three pieces in this big picture of the proof that I didn't go through. The first one is the concentration bound, which I'm not going to prove, and the other two are these two, pool size bounds, and I'm going to give you some intuition of how we can prove these bounds now in the next, hopefully, 2 to 3 minutes of this video. Let's start with the first one, which is the greedy bound.